Good morning, my dear J Warriors. This is your Captain Shreyas, and welcome to the Vedantu J English channel. And today we are going to start the very interesting and sweet and very straightforward chapter of electromagnetic waves, which guarantees one question in your JEE Mains examination. In the last many years, you open up any year, you will see that one question from electromagnetic waves is there. And it is very simple. So I am pretty sure this next 2-3 hours, which you're going to spend with me, is going to be very fruitful in your upcoming JEE Mains exam. So electromagnetic waves, we are going to start off with Maxwell's equation, the displacement current, modification of Ampere's law. Then we are going to go to the electromagnetic wave equation, then the speed of light formula, energy related questions, intensity related questions, and finally the electromagnetic spectrum. Okay, so that's the flow of today's lecture. So it's going to be a detailed one shot marathon. All right. But since the chapter is not too big, it will not be 4 or 5 hours. It will be, I think, around 2 to 3 hours. Okay. So this is my quick introduction slide. If you are new to the channel, please subscribe and join the channel so that you do not miss any academic content and all the important updates. And yes, if you have subscribed, mark your attendance by liking this video. Okay. Hi, this is your Captain Shreyas. Welcome aboard, guys. Hi, Lewis Hamilton. Oh my God. Wow, what name, man. I love it. I love it. I love it. But why there is no Max? I want Max too. Max is my favorite. Yes. Hi, Sudarshan. Hi, Sabrinathan. Hi, Naveen. Hi, Madhumita. Welcome. Hi, Pritija. Good morning. Good morning. Hi, Ibu. Nice to see all of you guys out here. Hi, Bhavyashri. Good morning. Good morning. Good morning, Sweta. Hi, Drawn. Welcome aboard. So it's time to begin the lecture. Yeah. Hi, Padma Suresh. Good morning. Nice to see all of you. So let's begin with the class of electromagnetic waves. See, light is a very interesting, forget about physics, forget about chemistry, forget about JEE. In as a subject as a whole only, it is very interesting because it's very mysterious, very colorful, and lot of theories of light have come for ages and ages together, and still people haven't understood light completely so much. But yeah, we are very close to the end, but not there yet. So right from Newton, who thought light was a particle, to Huygens, who said light was a wave, which we studied in light waves chapter, to then the modern theory which we study is the dual nature of light, where light behaves like a particle sometimes and like a electromagnetic wave sometimes. This electromagnetic nature of light was given by somebody known as Maxwell, and Maxwell is a great person, great scientist. He has given those famous equations which we are going to study, called as the Maxwell's equation, which revolutionized everything, right? Specifically in the field of electromagnetism. So you can also call Maxwell as the godfather or the father of electromagnetism, because he has given some crazy equations and he proved that light is an electromagnetic wave. So these beautiful colors that you see, from red to blue to orange to yellow to purple to indigo, these are nothing but different wavelengths, and these wavelengths decide, what kind of color I'm going to see. But unfortunately, we see only a very small range of wavelengths, which we call as the visible spectrum, from around 400 nanometers to 700 nanometers. Below 400 nanometers, we cannot see, and above 700 nanometers also we cannot see. This is infrared, that is ultraviolet, and many other animals apparently can see such spectrums, can see those wavelengths. So we, in our scope, can barely see 400 to 700 nanometers, and in that only we get so fascinated. We click pictures, we upload those pictures, and we enjoy the world around us just with these few wavelengths. But it is also an interesting thing to imagine and talk about how would the world be if someone were able to see all the wavelengths, right from 0.000000 whatever meters, or almost 0 meters, to almost infinite meters, basically the entire spectrum. So that would be a crazy colorful world. It will feel like you are hallucinating. But maybe God has limited us for a reason, so that, always something should remain mysterious. Anyways, now let's talk about the origins of how this electromagnetic waves and theory came. So for that we need to go back a little bit to Ampere's law. I know this is going to magnetism chapter, but still, there is a small part which you should be aware of. Recollect the chapter of magnetic effects of current, and we have studied that if you have a wire which carries current, then it produces around it a magnetic field. A wire carrying current produces magnetic field, and using Biot-Savart's law or Ampere's law, we know how much this particular magnetic field is going to be. So our Ampere's law says that you can use magnetic field dot the path length vector and do this integration over the entire path, and that will be mu naught multiplied by the current inside. Using this, you will get the magnetic field at any location on that away from that wire as mu naught into current divided by 2 pi multiplied by r. This is what you get the magnetic field as using Ampere's law. Very simple and straightforward. Now, when I write this particular I over here, this I represents the current which is piercing through that particular loop or that path, imaginary path. So for me, this is that imaginary path. This current is piercing it. Now, what do you really mean by the word piercing? Because till now we never really focused on this word. We understood how it is going inside of it. So yes, it is piercing. What really piercing means? Does that mean that if I imagine a film, a soapy film, just imagine this imaginary loop was immersed in a soapy water and you take it out, there is an imaginary film, and that imaginary film is now being pierced by this particular current carrying wire. I can see that soapy film is being pierced by that current carrying wire. That is what piercing is. Exactly. That is what piercing actually means in this context of Ampere's law. Then I have a doubt in this. Is there a guarantee that, or is it necessary that the film should be flat? Can it be curved, more curved, curved on the other side? And still, will I call it to be pierced? The answer is yes. Because even if it was flat or curved, whether the wire pierces here or whether it is curved and the wire pierces somewhere in the front, or whether it is curved like this and the wire already has pierced here, it doesn't matter as long as it is piercing. See, even if this soapy film was like this, okay, even if this particular soapy film was like this wire would eventually pierce it. It's not like the wire stops in between. It's an infinitely long wire. So the wire will eventually pierce it, whether the film was this way, concave, convex, or even flat. How many of you agree with this statement? Let me know in the chat box by putting up a thumbs up. Yeah, it can be of any shape. Correct. Very good. So, Ampere's loop law, I don't think it is visible over here, is consistent, meaning it is valid, it is true in all the cases, whether you take a film which is flat like this, or even if you take a surface which is like this. This is a soapy film like this. Once again, yeah. So this is something like this. Just visualize. See if you're able to visualize this. So whether the sheet is like this or the film is like this or whether the film is like this, eventually this particular wire is going to pierce it. We know that this particular wire is going to pierce it somewhere or the other, and you can see it goes inside and eventually it pierces right over here. Okay, it pierces right over here. So the Ampere's loop law is always consistent. Everybody understands this. Great. Now comes the next part of this. Imagine as this wire is carrying that current, imagine something like a capacitor or some two plates basically which are charged. Now, if there is current flowing, the capacitor will store the charge positive and equal amount of negative charge on the other side, and the current will continue and it will be there in the circuit. Because if current is coming in, the current should also be going out. And I have not drawn the other part of the circuit, but there is a circuit outside of it which is there, but it is not necessarily shown. Point is, the current is going out and coming in, going out and coming in, and the charge on the plates is changing because of the current being drawn or being put inside of it. So the point is now, if I apply the same logic, because Ampere's loop law is valid no matter how you take the film which is being pierced by that current carrying wire, whether it is flat or curved. So the same logic should be applicable over here, and I should be able to say, instead of taking this flat film which is being now pierced over here, instead of taking this flat film which is being pierced over here, because after this I should show ideally a dotted line, I will take a curved film, something like this, maybe in this shape. Even for this, Ampere's loop law should be valid, isn't it? Ampere's loop law should be valid. But there is a problem in this the moment you do that. Can you guess what the problem is? Can you guess what the problem is? The moment I take my film curved like this, I find that there is actually no current which is being pierced. How many of you are able to visualize that? How many of you are able to visualize that? Put me a thumbs up in the chat box. Yeah, this wire is carrying current till here. In between these two plates, it's empty space. There are charges. There is no actual current which is going. It's just the electric field which is going positive to negative. And from here, actual electrons are flowing. So current is the flow of electrons. So there is no electron which is really physically moving between the plates of the capacitor or those two plates. How many of you are able to see it? Let me know quickly in the chat box. Yes or no? Very good. Yeah. So then the question arises, what is the current which is piercing? The answer is nothing. So if there is no current which is piercing, so the right hand side of Ampere's loop law, current will be 0, RHS will be 0, this will be 0, magnetic field will be 0. So the magnetic field, by that particular method where you choose the film which is being pierced to be of a curved manner, because there is no current only which is piercing it, the magnetic field turns out to be 0. Now this is the problem which arises now, because how can the choice of this film decide what is the magnetic field? If there is a magnetic field at this point, and I know it is mu naught I by 2 pi r, it has to be mu naught I by 2 pi r, whether I take this film like this or like this or like that or like that. Because the film was a choice. It was not a compulsion. Whether Ampere's law is there or not, magnetic field is there at this point. So, just because I have changed my film, how can this choice of the film say that magnetic field is not there? Because the current pierced, because the current which is being enclosed by it, or the current which is pierced by it, is basically 0. Whereas in this situation, when I take the film like this, you can clearly see till this point it is going, and after this it is behind that film. So the current which is being pierced is definitely not 0. In fact, it is I. So there is something wrong in Ampere's law, or something which we are missing in Ampere's law, I would say, because the choice of a film should not change my magnetic field's outcome. The magnetic field, if it was mu naught I by 2 pi r, irrespective of the shape of my film which is being pierced by the current, it should be the same. This is the premise of the next part, which is the theory. How many of you get this? Yeah, you can watch this for CBSE also. Yeah. Abhishek, don't spam or else you will get timed out. Yeah. So just to summarize till now, Ampere's loop law we have been using till now, but today we are discussing what is the meaning of the current which is inside of this enclosed. It means whatever path you have been traveling, if you cover it with a film, it should cut through that film like that. But that film can be of any shape and size as long as the wire will pierce it somewhere or the other. So ideally, the choice of the film shape or size should not matter. So Ampere's law should be consistent. But the moment there is a break in the wire, meaning something like a capacitor, and I choose the film to pass between those plates, which is that empty gap, that's where the inconsistency arises. And I am forced to think whether my Ampere's loop law is actually correct or some modification is required. And the answer is we need some modification, without which we cannot apply it. So let's think what should be that modification. Where was the problem coming? The problem was coming the moment the film is passing through that empty gap, but still there is magnetic field here. I know this is wrong. It can't be 0. So current pierced is coming out to be 0. So should I by force say that no, current is not 0, current is there? Because that will change my whole definition of current. Because I know actually there is no current here. Actually speaking, there is no motion of electrons or protons between the two plates of the conductors. So there has to be something which is like current, but it is not current, which is like current, but it is not actual current. It is producing magnetic field. Remember, magnetic field is produced by something like current, or basically current, but the problem is there is no actual current here. So there has to be something which behaves like current, which produces the magnetic field, and which is being pierced by this film or this sheet, imaginary one, and I would be able to apply Ampere's law. So that imaginary current which is piercing that film, which produces the magnetic field, and which makes the Ampere's law look okay, that imaginary current is then called as the displacement current. It is not the real current, which is the conduction of electrons, uh, you know, do it. It's not the conduction current. It is a current which is produced because of this electric field which is being generated. So the electric field piercing, electric field is an imaginary quantity, remember that? So the electric field which is piercing through that film is creating that displacement current. What is it called? Displacement current. So displacement current, it's a fictitious current, like pseudo force. It was not a real force, but chumma we put it to, satisfy Newton, bro. Like, okay, bro, listen, your law is not valid. So here, take this pseudo force and now you be happy. Chill, madi. So we are saying this is a fictitious, like a pseudo current, which is not because of the flow of electrons. But the moment you take the film, which is passing, the moment you take the film, which is going to pass through the electric field, or basically that empty space, then that electric field which is piercing through it will cause the displacement current. will cause that particular displacement current. The question arises, how much is the value of the displacement current? That displacement current is permittivity. Yes, 8.85 10 to the power minus 12 multiplied by d phi by dt, where that phi is the electric flux, not magnetic flux. If you get confused, now is the time to again rethink. Remember, Faraday's law was EMF is d phi by dt magnitude wise, but that phi was magnetic flux. So when magnetic flux changes, it produces electricity. When magnetic flux changes, it produces electricity. That was Faraday's law. This is exactly opposite. When electric flux changes, when electric flux changes, that is producing current, which in turn produces magnetic field. This is crazy. It's like an interlinked phenomena. When magnetic flux changes, Faraday says electricity is produced. This law is now saying when electric flux changes, current is produced, because of which magnetic field is produced. So electricity producing magnetism, or magnetic effects producing electricity. All of these are possible. All of these are possible. That is the beauty of electromagnetism. That is why the unit also is called electromagnetism. Earlier, people used to think electric force is separate, magnetic force was separate, but Maxwell brought all these people together. He said, listen, electricity and magnetism are not separate forces, they are actually one thing only. Electricity can create magnetism, magnetism can create electricity. So the displacement current is permittivity into rate of change of electric flux. Electric flux. And if you have forgotten what was electric flux, just putting up the simple formula for it. So it is nothing but the electric field dot product with the area, and the SI unit, and the SI unit and the SI unit for electric flux. This is volt per meter into meter square. So it will be volt meter. SI unit of electric flux is voltmeter. So that is your electric flux. So that is basically your electric flux. And that creates your displacement current. Okay. Everybody till this point, absolutely clear, my dear students? Okay. So now you might be wondering, so sir, tell me what is actually Ampere's law? Is that modified now? What is it exactly going to be? Well, I'll tell you something. Maybe there is an actual wire which is going over here, which has some current, let's say IC. And because of that electric field which is over here, because of that electric field which is over here, electric field which is over here, you will see that electric field, when it changes, the flux will change, that will cause the conduction current. So if somebody decides to take something like, say for example, they decide, okay, this is my loop. They decide this is my loop. Okay, they have decided this is the loop or the path which they are going to travel for applying Ampere's loop law. For applying Ampere's loop law. Now, this is an actual wire which is carrying current. This is your actual conduction current, actual conduction current which is flowing. What is flowing here in between these two plates? What is flowing here in between these two plates? Because of the electric field changing, because of the electric field changing, that is basically your displacement current. That is basically your displacement current, whose symbol we call it as ID. Whose symbol we call it as ID. So then when I take any random point, and there might be some magnetic field over there, and I'm moving some small distance over there, dl, and I keep moving across that particular path. This is the closed path, basically. This is a closed path. This is a closed path. Then the modified Ampere's loop law becomes something like this. Cyclic integral because I start from a point and I return back to the same point. That's why the closed integral or cyclic integral. Magnetic field vector dot dl vector is equal to, now observe carefully, you have mu naught over here, but you have mu naught over here, but there is a change. You will have two kinds of current. One will be your regular conduction current, IC, and the other one will be the displacement current. So it is the sum of both the currents. So it is the sum of both the currents that should be there inside the brackets multiplied with mu naught. That's it. So this is the modified Ampere's loop law. That's all. This is the modified. This is the modified law. This is the modified law. This is conduction. This is displacement. Okay, is this absolutely clear? So conduction current is that actual current which is passing. Displacement current is the current which is produced by the changing electric flux with time. If the flux is constant, it will not create, remember, only when it changes, just like magnetic field changing produces electricity, electric flux changing produces magnetism. That's what it is. Okay, isn't it fascinating, guys? Yeah. So now we have the complete equation, which looks something like this. Magnetic field dot dl is mu naught into IC plus ID. ID is nothing but epsilon naught d phi by dt. Okay, this is your displacement current. Okay, so finally we have all the four equations which were given by Maxwell. So he put it in a beautiful form. Gauss law in electrostatics, electric field dot area vector, here S stands for area, is charge inside by epsilon naught. But if you do a similar thing in magnetism, magnetic field dot area vector, the answer is always going to be zero. Net magnetic flux is zero. So that we have studied in magnetism. This was also the proof that magnetic monopoles do not exist. Magnetic effects always exist in the form of dipoles. So whatever flux goes out has to come in. So this proves that you cannot have just a source of magnetism or just a sink of magnetism. Whatever magnetic field lines are emitted, they eventually come back, and there is no start or end to the magnetic field lines. So this was that law. Magnetic field flux is always going to be zero on a closed surface. This is electric field flux on a closed surface is the inside charge by epsilon naught. Then you had the Faraday's law, which was rate of change of magnetic flux is negative times, negative comes because of length, is the induced EMF in the circuit. The EMF is E dot dl. Okay, electric field into the length is nothing but the voltage. So the integration of electric field into the length gives me the voltage in that particular loop. So that is the simplified version of that. Then the Ampere's loop law, which we just studied, magnetic field into the length vector is mu naught into the conduction current plus mu naught into basically that displacement current given by epsilon naught d phi by dt. So this, they have opened up the brackets in this term, nothing else. So if you write it in the expanded form, mu naught into IC plus mu naught into ID, you will exactly get that, right? So it's just, you open it up. So mu naught into conduction current plus your mu naught into the displacement current. The displacement current will be permittivity into rate of change of electric flux. So you open it up like that. That's how it will look. Is that right, everyone? So these are the four important laws. See, the first two laws here, both are integration with areas. So the integration of area gives for electricity charge by epsilon. For magnetism, it is zero because there is no net magnetic charge inside. For length integral, this is Faraday's law. Here it is Ampere's law. That's the only difference. So first time you are integrating with area, second time you are integrating it with length. All the integrals are closed integrals. Okay, meaning you are taking the entire surface or you are taking the entire loop, okay, every single time. So these four laws should be there in your head. Yeah, yeah. Lens gave that negative. Yes, correct. Now, just to reaffirm this particular concept again, if I choose now, coming back to our original problem statement, if I choose this as my area, then if I choose this as my area, then I will have conduction current, but I will not have displacement current. How many of you agree with this? Because actual current is passing through it. Actual current, actual current will be passing through it. Is that right? And not a fake current. So you will say that there is conduction current, but there is no electric field here. So displacement current will be zero if you choose this flat surface for piercing. But if somebody chooses, this particular area, if somebody chooses this particular film for the piercing part, then that person is going to say that the conduction current is zero, but the displacement current is not zero. Displacement current is not zero if that person is choosing that pink shaded area. How many of you are able to visualize this now? Because here actual current is not there, but your only electric flux is flowing through it. But since the magnetic field is always going to be the same, so always you are going to get the same magnetic field, whether you choose this or that, same magnetic field. So whether you choose this area or whether you choose that area, the magnetic field is going to be the same. It just means in this scenario, whatever current is going here and the displacement current which is there, magnitude wise, they are the same. So one can say in this scenario, conduction current is equal to the displacement current. But keep in mind, first time in the first scenario, there was conduction current, but displacement current was zero. There was conduction current, but displacement current was zero. In the second scenario, the conduction current was zero, displacement current was not zero. So both of them have to be equal. That is the final conclusion. Both of them have to be equal. So the conduction current will be equal to the displacement current, irrespective of what you are choosing the shape of the film to be. Displacement current will need changing electric flux. How that electric flux will change? Because of changing current. So displacement current does not need changing current necessarily. If somehow you are able to change electric flux, that's enough. Whether by actually physically somebody is putting charges or by changing the current, doesn't matter. What it needs is changing electric field lines. That's what it needs. Not necessarily changing current. Yeah, changing the current can also produce changing flux, which can also create displacement. Crystal clear? Everybody? I don't think anybody would have told you all these things in intricate details, because if you go through NCERT, the concepts are so confusing. You will forget it, you will not even understand it, and you will not even develop the love or affection towards whatever is being taught. So that was your thing. So our problem is solved. Ampere's law is consistent whether I take this area or that area. Even if I choose an area over here, what I missed in this scenario, which gave me, current as zero, what I missed was actually the displacement current. So if I take into account the displacement current, my job is done. Okay. So let's see some questions coming up on your screen, and here it is. The displacement current due to time varying electric field is given by, what's the value of the displacement current due to time varying electric field? Guys, if you've forgotten to like the video, please like the video right away, right now. Yeah, it's very simple, just takes 1 second. Do it right now. Many people forget to mark your attendance, and if you've forgotten to subscribe, even Now you have not subscribed means really slow claps for all of you. Come on, subscribe. Yeah. Okay. So now I have not confused you, Ridan. Now I think it is there in your head. I'm so glad. Yeah. Option B for IT Bombay. This question, by the way, came in JEE. JEE Mains asked this question. Can you believe that? Epsilon naught d phi by dt. Now you know permittivity will be there and rate of change of electric flux, because electric flux is there. Electric flux is associated with electricity, permittivity, charges, right? So epsilon naught is there. Many people get confused in the exam and they write mu naught, or that they put epsilon naught mu naught into d phi by dt. Lot of things they get confused. But I'll tell you why this confusion also happens. It happens because you are trying to remember some weird formulas like this expanded formula. So here epsilon naught mu naught is also there. So you're thinking this whole thing is displacement current. No, only this much is displacement current. Actually, total current is this much, which is multiplied by mu naught. Okay, so that was the catch. Now it looks simple because you have studied the topic fresh, but in the exam, everything looks confusing. Yeah, A looks like B, B looks like D, C looks like S. All these things happen. If the electric flux changes at this particular rate, then the displacement current in milliampere is how much? Displacement current in milliamperes is how much? Well, the displacement current formula is permittivity into rate of change of electric flux. Okay. Now, I think permittivity value, we can just put it as 8.85 into 10 to the power minus 12. This particular thing has already been given right over here, rate at which electric flux changes. So it is 0.1 into 10 to the power positive 9. So that will give me 8.85. 8.85 minus this 0.1 is also there. So I'll put 0.85. So I'll put 0.885. 0.885 and minus 12 and plus 9 will make it minus 3. So 10 to the power minus 3. This will be in amperes. If you want, because it is in milliamperes, so 0.885 milliamperes. So that should be the answer. This can be an integer type of question. They can make it look like an integer anyhow. So the answer is 0.885 milliamperes. Yes, very good. Amazing, amazing, amazing. Very good. Awesome. Moving on to the next question on your screen. The displacement current is 4.425 microamperes, which is developed in the space between a parallel plate capacitor. Yes, it has to between two plates of a capacitor. Okay, it's not a real current. And the voltage is changing. The area of the plate is given. The distance is how much, and the value of X is asked. Permittivity is also given to me. Okay, so I will look at the problem like this. These are the two plates of the capacitor, and we have electric field which is being generated, and that will cause electric flux which will change, and that's how you have to figure it out. Okay, so how much is d phi by dt? Let me think. Or another way of looking at it is my displacement current, my displacement current will be equal to whatever current is entering inside, because this will be positive plate, this will be negative plate. It will cause a displacement current. That displacement current will be equal to that conduction current. So I can put ID will be equal to I conduction, and the I conduction is basically I, and this I is rate of flow of charges, dq by dt. So I can make it as d by dt. Charge is capacitance multiplied by voltage. So did you understand why I did this? I just explained it to you right over here. Whether I take this area or that area, when I take this area, conduction is there. When I take that area, displacement is there. But since the outcome is the same, so this choice should not be affecting me. So hence, both these currents numerically should be equal to each other. So in both the scenarios. So that's why I said that, the displacement current is equal to the conduction current. That was the first trick which I have used. Second thing which I have used is current definition is dq by dt, okay, which is C into V. charge is capacitance into voltage. Capacitance will not change. It is a constant thing. So I can just put capacitance outside and I will have dV by dt. Now I have an idea. I will write it down like this. Capacitance is permittivity epsilon naught area divided by d, and dV by dt, I don't have to do anything. I'll just leave it as it is. So this is my displacement current. So the question was to figure out how much D is. So D, if I take it on the top, permittivity into area divided by the displacement current into dV by dt. Okay, perfect. So epsilon naught is 8.85 into 10 to the power minus 12. Area of the plate is 40 centimeters square. So 40 into 10 to the power minus 4 if you convert it into meter square. And the whole thing is being divided now by the displacement current, which is 4.425 micro. That means 10 to the power minus 6 into the rate of change of voltage, which is 10 raised to the power 6. Okay, let's see what and all things will get cancelled. This I think is divisible. For 44.25 into 2 will give me 88.5. So this will go 2 times basically. Okay, this minus 6, this will cancel with over here. This will become minus 6. All right, is that right? Okay, so we have a simplified form. 2 into 4 is basically 8 multiplied by this minus 6 and plus 6 will also cancel. You can see that right over here. This minus 6 and plus 6 will also cancel. So 0 and minus 4 will become minus 3. So this will become 10 to the power minus 3. So the distance between the plates of the capacitor is 8 into 10 to the power minus 3. So the value of x is going to be 8. That is the answer. Yes, it is the correct answer. It is the correct answer. So sometimes a question might look complicated, okay, especially like this for displacement current, but you might have to use some knowledge of capacitors or current electricity and whatever you learned here. This is one of the most complex questions of displacement current, by the way. Okay, awesome. Now will you be able to solve any kind of question on displacement current, guys? Have you understood this concept of what this displacement current is and what this Maxwell dude has told us? Okay, and how this works exactly? Okay, this is very, very important, guys. You take any imaginary area, there will be a real current called as conduction current, and there might be a hypothetical current which is called as displacement current due to electric field lines which are changing within that film. Okay, that's all. So that is the modified Ampere's Maxwell law. Now, this much is enough. After that, we now go to the main part of this chapter, which is electromagnetic waves. Why did we do all of this? Yeah. Yeah, in JEE Mains. Yes, yes, correct. The reason why we did it is because to explain why electromagnetic waves are generated, only for that, nothing else. And to make you understand why a light is an electromagnetic wave, why can't it just be an electric wave? Why can't it just be a magnetic wave? I mean, you would have thought about it. If you're not thought, at least think now. It could have been just an electric wave, isn't it? Why that magnetism has come in a light wave? Or why can't it just be only a magnetic wave is going? Why can't it just be one of them? That's the problem. See, I'll tell you what. If a charged particle is at rest, like you take an electron, it will produce electric field around it. You move that electron, then it will create electric field also and magnetic field also. Remember, if you take a charged particle, obviously its electric field is there, but a charged particle moving is nothing but like a current which is flowing, and a current will always create magnetic field. And now you accelerate that charged particle, that is crazy. You're not just making it move at a constant speed, accelerate it. That electric field, magnetic field, all of them will keep changing with time. It will not be like constant also. At least if it was at constant speed, you know, okay, things will be uniform in nature. But in case of accelerated motion, it will create changing electric fields and magnetic fields. Now, what is the problem with a changing electric field? What will it create? Answer it in the chat box. What will What will changing electric field create? Changing electric flux. What will changing electric flux create? Magnetic field. Correct? So now you have your answer. Similarly, if you have changing magnetic field, what will it create? Magnetic field is changing. Then I know, sir, Faraday's law, Faraday Lenz's law. Yes, it will create electric field around it, which is basically electricity. So electric fields changing create a magnetic field. Magnetic fields changing create electric field. So they both create each other. That is why you cannot just have a electric wave or a magnetic wave. Because you have an electric wave, electric field is changing, it will naturally create a magnetic field around it. You cannot just have a magnetic field wave, because a magnetic field which is changing like a wave will automatically end up creating an electric wave. So they both will coexist together. They both will coexist together. And that is why you have an electromagnetic wave. So an electric field creates magnetic field creates electric field, and that is why you have an electromagnetic phenomena. So if you ask me how to create an electromagnetic wave, all this while you are taking it like granted. Electromagnetic waves, it is there everywhere, no? Sir, this light is there. From sun it is coming. My body is also giving electromagnetic wave. Sir, the Wi-Fi signal is also electromagnetic wave. Sir, my phone is also using electromagnetic waves. My radio is using electromagnetic waves. So all this time you are surrounded with electromagnetic waves. But the moment you are learning this theory, suddenly you start thinking, oh, how is this electromagnetic wave being created then? How do you create these changing electric fields and magnetic fields? The answer is simple. You take a charge and accelerate it. You take a charge and accelerate it. But if you want to create it periodically, you cannot just take a charge. Hey, sir, take catch. Oh, what? I took a charge and now you have to accelerate. I have to accelerate. I have to keep running. No, you don't do that. Instead, what you do, you make the charge go back and forth. You make the charge go move back and forth. It's enough. It is like an oscillation. It is always accelerated motion, right? And it will create electromagnetic wave in periodic manner. Is that right? Everyone. So you just take a charged particle or particles and make them go back and forth. Don't run with the charges. Don't run away, because then you have to run infinitely with continuous acceleration, which is madness, which is not possible, because someday or the other you will reach the speed of light. Not possible. So that is why you take the charge and make it go back and forth, and it is creating electric field, and also it is creating magnetic field. You have now an electromagnetic wave. That's it. So at the end of the day, all your mobiles, your laptops, your radios are nothing but oscillating charges, and that is all which is creating that light, if you think about it. That's all. At the molecular, at the minutest of the minutest level, at the end of the day, all the light, all the electromagnetic waves, Wi-Fi, mobile, radio, infrared, ultraviolet, anything that you see around you is, at the end of the day, because of the motion of the charges. That's all. Isn't it interesting, guys? And how does that electromagnetic wave look like? It looks beautiful. Something like this. And this keeps moving. The green one is the magnetic field, the red one is the electric field, and they both are perpendicular to each other. They will not be in the same plane. They will not be at a small angle, 30 degree, 20 degree. No, they are at perpendicular directions. And they will keep moving. Electricity is creating magnetism, magnetism is creating electricity. Their wavelengths have to be same. Frequency has to be same. Speed also has to be same. How is it possible that electric field is moving faster? Magnetic field is like, oh, wait, man, I'll come, I'll follow you, you go. No, it will not happen like that. Even their wavelengths have to be the same, because in one time period, your electric field has changed. Magnetic field also should complete one complete period in that same duration. Wavelengths, speeds, frequencies are the same, and they are also going to go in the same direction, just that the variations are going to happen in mutually perpendicular directions. So if electric field oscillates in the y-x plane, example, the magnetic field will oscillate in the xz horizontal plane. If it oscillates like this, it might oscillate like this. If it oscillates like this, it will oscillate other thing will oscillate like this, always in mutually perpendicular planes, right? Very good, Vedan. Okay. Uh, Arivarasu, yes, I'm very disappointed, but that is the rule of life, no? That is why not every student gets above 200. Actually, it was very simple for all the students to get above 150, 180 marks. All you had to do, Shreyas Sir is there. You have the best teachers. Shreyas Sir has got full marks in JEE Physics when he wrote his JEE exam. You are the best teachers. You just had to attend the class. But if life was so simple, then everybody would do very well in life. And that is the reason why not everyone does very well in life. So I feel very disappointed. Yes, very true. Because for me, all students are equal and I want every student to study. I want every student to do very well, and especially the students who do not have access to English lectures in south of the country, because you do not have any channel which is dedicated for JEE. You have other channels, but JEE related content, that level of content is not there. So I feel very sad. But what to do? It's okay. At least I have some thousand students or 100 students or 10,000 students who might be watching me live or recorded, and they will do well in life, and they come back next year and they will tell me, sir, I got into this college, and I am pleased with that. Yeah. Okay. Sir, can large bodies, if charge and accelerate, create EM waves for a short period of time to then linear acceleration? Yes, yes, yes. Even if you take a big body which is charged and suddenly you give it a jerk, for that brief moment, it will create an electromagnetic wave for that small moment. Yes. All right. Okay. Now, what are the wave characteristics? Number one, there is electric amplitude, magnetic amplitude. Electric amplitude is called E naught. Magnetic field amplitude is called B naught. B for magnetic field, so B naught is the amplitude. E for electric field, so E naught will be electric field's maximum value. Lambda will be the wavelength. All the waves will travel at the speed of light. Okay, that's standard. So some basic properties will go through it. It is very theoretical. I'm pretty sure you know about this. Still, electromagnetic waves do not require medium, which is obvious. The light from the sun travels so many lakhs of kilometers, but there is nothing in between. It's vacuum. But even if there is something, it does not matter. Yeah, it will become slower, but it can still travel inside a medium. But medium is not a necessity. Even without medium, get lost. I am light. I can travel. Okay. These waves travel with the speed of light in vacuum, but the moment they interact with matter, their speed reduces. But otherwise, their speed is very large, 3 into 10 to the power 8 meters per second. So I can just put it over here. C value, which is the speed of light, 3 into 10 to the power 8 meters per second. These waves are transverse in nature. We saw that right over here. These are transverse. The oscillations are perpendicular to the direction of the travel. In fact, you should also be aware that this particular plane, which is there, is called as the plane of oscillation of that electromagnetic wave. This is your plane of oscillation, plane of oscillation of that particular EM wave, which is used for polarizers. So when you use a polarizer, there is a plane of oscillation which you consider, right? So that plane is always the electric field's oscillation which is being considered. You could have chosen magnetic field, but one thing you have to choose. So we choose electric field's oscillation as the plane of oscillation. Next thing, they both carry energy as well as momentum. Obviously, if electricity is there, magnetism is there, they will carry energy with them. But this momentum part is not so obvious, guys. You might think, oh yeah, come on, yeah, momentum will be there. No, it is not that obvious. That momentum part comes because of dual nature of light, and you study that in modern physics, which is photon. So the photon is that particle nature of light which is carrying the momentum part. Remember, momentum of light is h by lambda. Yeah, that is that concept. They can be obviously reflected because light can get reflected. They can be also refracted, so they will bend. They can be also absorbed, so they fall on something and they get completely absorbed by the atoms. Definitely. Frequencies are inherent characteristics. So when it travels from one medium to other medium, the speed and wavelength will change, but the frequency never changes. So this you would have learned even in ray or wave optics, that when light will change the medium, then the frequency will remain the same. It's just that the wavelength and the speed will change. So frequency is always constant. It is an inherent characteristic. It is something which you cannot change. Like if you are Pandu, you are Pandu, whether you go into class, whether you go into college, whether you are at home, whether you are at a friend's house. But yeah, your other things might change, your behavior might change, your something, I don't know, the way you interact might change, but other, your name is the same. So same way, light is being identified by frequency, not just wavelength, because wavelength can change if the medium changes. Keep that in mind. Okay, are all these points clear? Let me know in the chat box. Do the EM waves lose energy while traveling? They can lose energy while traveling if they interact with matter. But if they are traveling in vacuum, there is no way the electromagnetic waves will lose energy. They'll just keep carrying that energy into the vast space of that empty universe until they meet someone, and there they will lose energy. One thing is that the energy is not confined to a particular region. The energy will slowly keep on expanding. So the energy per unit area will reduce. So the intensity of the light reduces. So if you are asking me energy, is it lost while traveling? The answer is no. But intensity is generally lost. And the reason for that is because the light will spread. And once the light spreads, the energy per unit area will be reduced. So intensity reduces, not the energy. Yeah. Do they carry the matter? No, they do not carry the photon. The photon is just a concept again, which comes into play with the moment you have interaction with matter. So as long as they are traveling, how they are traveling, nobody knows. Are they traveling like a wave or they are traveling like a particle? The experiment decides whether they are behaving like a wave or a particle. So light is, that's why I said it's a very mysterious characteristic, mysterious thing. When you perform an experiment, that experiment compels the light to show one of the two behaviors. Okay, so if you are performing a refraction experiment, or you are performing diffraction experiment or interference experiment like Young's double slit, light will show its wave nature. But if light is falling onto a surface, it is hitting the surface, it will apply some momentum impulse force, then light will show particle behavior. But when it is moving, I do not know whether light is moving like a wave or a particle. So the experiment decides what is it going to show. Okay, it is very crazy to think about it. It is not so easy to understand. Okay, how many of you did not understand this? Let me know. If you did not understand it, that means you have understood it. Because light is very mysterious, guys. That's what I'm trying to tell. If you have understood light in your regular classes, then 100% your teacher has not taught you properly. The only way you can understand light is when you do not understand it, because it is very, very mysterious. Light is not revealing its true nature to us. The only way it reveals us what it is when you actually perform that experiment. That experiment decides the nature of the light. Yeah. Hello. Hi. Awesome. Yes, the life of a photon is instantaneous, instantly generated. Perhaps the sun, the next instant it is in our eye. Very true. It's just crazy. So just imagine the light which came from the sun never knew what it is, what its future is. But light is coming and I am up for a surprise. I suddenly perform Young's double slit experiment. Light is like, hey, I'm a wave. Wow. Then you are like, okay, now I'm going to fool the light. Light is a wave. Okay. Light is coming. And then I take a surface and I perform photoelectric effect. Hey, light, you are a particle. So, when the light left the sun, it really didn't know what it was. Was it a particle? Was it a wave? What experiment is waiting for me on the earth? It knew nothing. But the moment you change the experiment, I mean, the whole past of the light, the past tense of the light has changed. So, some scientists also say that you can change the past of a light by performing the experiment suddenly. But it is different story. We will not go there, like how you can change the past of a light by performing the experiment. Okay, but I think you would have got some idea, because the light had no clue of what you are going to do. Anyways, let's do the simple questions. JEE is very simple, guys. I mean, this theory, if I keep talking, right, this will become a big 7-hour marathon. Okay, and we'll have crazy discussions, and then maybe we'll need coffee and maybe some biscuits, and then we will also relax and maybe we'll watch a movie, and then we'll have more discussions on light. And that is an endless story. But today we have to solve some questions. Select the wrong statement. Electromagnetic waves do not require any medium for their propagation. Electromagnetic waves can travel through vacuum. Material medium is necessary. Electromagnetic waves are transverse in nature. What do you think? Okay. Yeah. What is the answer, guys? Select the wrong statement. C for Captain Shreyas says Ratna, Ridan, everyone. Is that so? Pakka? Guarantee? Lock kiya jaye? Okay. Material medium is necessary for propagation. That is wrong. You don't need material. Material is there, okay, bro. I will still go through you, but I'll go a little bit slowly because you are matter. But otherwise, I can still travel. Don't underestimate the power of a common man. Okay. Electromagnetic waves are transverse 100%. Electromagnetic waves can travel through vacuum. Yes. Electromagnetic waves do not require only any medium. Perfect. Next question. Which of the following is not true regarding an EM wave? Mainly statement based questions. They carry energy in electric and magnetic fields. They can exert force when they interact with matter. They can be deflected using electric or magnetic fields. They have momentum but no mass. Interesting. Which of the following is not true? Okay, come on, my dear students. Which of the following is not true? That's the question. Okay. They carry energy, yes, and it's an electromagnetic wave. Where will they carry it? In electric field and magnetic field, it's obvious. So first statement is true. They can exert force. They have momentum. So a momentum is being impressed on a matter. There will be impulse, and that impulse in that time duration will create an force. So force definitely is there. So that B is also correct. They have momentum, yes. No mass, yes. Electric field has no mass. Remember, it's a concept. Magnetic field also has no mass. So that's the funny thing about photon also. Photon does not have mass, but it has momentum. So D is also correct. Lot of people mark D. I have seen many people marking D. Wrong. They can be deflected using electric and magnetic fields. That is the wrong answer. So you cannot take electric and magnetic fields and deflect light. Not possible, guys. Lot of people think, sir, light is electric field and magnetic field. No, exactly. How can you apply force on a field? You apply force on a charge or a magnet. Remember, there is no matter in an electromagnetic wave. Getting my point? There is no actual mass or matter which has a charge or North Pole, South Pole. So that is why electric and magnetic fields cannot change the direction of light. Even a photon is chargeless, massless, so you cannot change its direction. In fact, in radioactivity, there is a radioactivity setup where alpha rays, beta rays, and gamma rays are coming. Alpha is positively charged, so it gets deflected by electric field. Beta ray is negatively charged, so it gets deflected in the other side. Gamma rays are uncharged photons, basically, so they go straight. That's how you know, oh, this is having some electromagnetic radiation. So, my dear students, they do not have charge, they do not have mass, so they can't be affected by electric and magnetic fields. Light itself is electric and magnetic field. It can apply a force on a charge. There is a difference. So, when light enters a material, there will be charges, protons, electrons. That electric field and magnetic field can apply force on those charges. So, light applies force, but it cannot experience force. It's a very strange thing. Yeah, cool. Let's move ahead now to the wave equations and other things. Just some time back, how many of you are loving this chapter till now? Yeah, loving it, guys. Isn't it very interesting? If you go through NCERT, you will sleep in the first paragraph only. I will guarantee you that. You can use it for sleeping in the night time. But don't do that. You have to read NCERT. It's very important for your boards and for JEE Mains. Awesome. Awesome, Sabri. Awesome, Ridan, Kangna. Awesome. Very good. Very good, Amra. Awesome, Rainberry got it. Great, you're correct, Remus Hamilton. Very good, very good. Very good draw with draw, was it? Drawn you Tamils. Oh my god, what is that name meaning? Chaotic chapter. Okay. So now let's talk about these wave equations. Now we are almost reaching the main part of the chapter. After that, there is hardly anything left. See, guys, any kind of wave equation, right? If you remember, any kind of wave equation which had some amplitude and which was traveling like this in some x direction. This is your y direction. Any point which is there, it will have some x coordinate and some y coordinate. The y coordinate or the y parameter which keeps on changing will be given by, you can write a, you can use sine also or cos also, doesn't matter. And then you put, you have k into x, then plus or minus into omega t. So this is your x. So y is a function of x and also a function of time. So this is your general wave equation that you get. Also remember, you use positive symbol means it is traveling in negative x. It is traveling in negative x direction. And if you use a minus symbol, then the wave is traveling in the positive x direction. In the positive x direction. So if you use a minus symbol, then the wave is going like this with this velocity. If you use a positive symbol, then it is going in the negative direction. It is always opposite. That is something which you should remember. This k is also called as angular wave number. K is called angular wave number, correct? And that k is nothing but 2 pi divided by lambda. Omega is called angular frequency. Angular frequency. So omega is 2 pi divided by time period, which is also 2 pi multiplied by the frequency of the wave. You can also write the wave velocity. You can also write the wave velocity in this form. So this wave speed or wave velocity, you can write it as omega angular frequency divided by angular wave number, which is also frequency into the wavelength, which is also frequency into the wavelength. So these were your general formulas which you have studied back in 11th standard in the chapter of waves. The unit of angular wave number is radian per meter. Radian per meter. This is radian per second for angular frequency. This is radian per second. Okay, so these are the things which I'm just trying to revise for all of you. Okay, from 11th standard, which will now be useful in this particular chapter. You can also write this as omega t plus minus kx. There is no necessity that k has to be in the start. K can be next term, omega can be first term also. It's perfectly fine. Instead of sine, you can use cos. If you use cos, it will not start from 0, it will start from maximum value. That's the only difference. So using sine or cos does not matter, but don't use tan. Okay. And this A outside is the amplitude, that is also fine. Sometimes you also write this equation in a slightly different way like this. Y is equal to A, then you take sine, and now what generally people do is they want to write, they take k outside, so they take that k outside and they write it as x, and you have your plus or minus. This omega by k will remain into t. Now, guys, what is this omega by k? Omega by k is v, right? Omega by k is v, right? So they also write this as like this, x plus minus Vt with the term k outside. This is also perfectly fine. It's just the same thing rewritten in a different form. Don't get scared. Suddenly, sir, but this is not looking like this. Array, it's the same thing, bro. Okay? There is no hard and fast rule. Great. Now, how does it look like for light? Because there is two waves, electric and magnetic, so we'll have two equations. Once we'll write for electric field, then we'll write for magnetic field. So for the electric field, in general, at any point, it will look like this, E naught into, okay, the same thing, okay. So it will be nothing but electric field is equal to E naught sine or cos, anything is fine, kx plus or minus omega t. E naught is the electric field amplitude, electric field wave amplitude, that's number one. Similarly, for magnetic field, we will write it down as B naught. If I use sine, I have to use sine. If I use cos, I have to use cos. If I started with k, I have to start with k. If I start with omega, I have to start with omega. Since I have started with k, I will start with k only. Kx plus minus omega t, same k, same omega, because same frequency and same wavelength. Okay, so this is your magnetic field wave amplitude, magnetic field wave amplitude. So let me just block them off. Very, very important formulas. And also, if you see, the light is traveling in this particular direction. See, for example, like this, light is traveling in this particular direction. This is the speed of light. How do I know light is traveling like this and not like this? There is a reason for that. Always remember the velocity of light, electric field, and the magnetic field at any point, any instant are all three mutually perpendicular. Not just that, if you take B hat, whether magnetic amplitude or just the magnetic field, you take electric field unit vector and the speed of light unit vector, they will always be like this. So you can write it down as C hat is equal to E hat cross producted with B hat. Check this out. If you take E, cross it with B, you will get the direction of light. So over here, I saw electric field was like this, magnetic field was like this. So E cross B is C. So it has to go this side. It cannot go along that side. And because it is going along negative x, technically there should be positive sign, but this is a general equation. This was just for representation purpose only. So I hope you understood how you decide the direction of light, E cross B. You can also use other things like, for example, B cross C is also going to give you E. So you can check this out. If I have to do E hat will be B hat cross producted with C hat. B cross C gives me E hat. Okay, so all these things are possible. Even if you take C and E, you will get B. Check this out. So B hat will be nothing but C hat cross producted with E hat. So all these things are possible. Main thing you should know, any one of these relation, specifically know this will be easier. C is equal to E into B, that is more than enough. Okay, C is equal to E into B. If you know that, it's more than enough. Anything else also you can do it, or if you know how this diagram works. Okay, this is very, very important. It's like I cap, J cap, and K cap. I cross J is K, J cross K is I. Yeah, remember that? So very similar to that only. Okay, okay, all right, very good. Okay, amazing, amazing. Yeah, it's the right hand thumb rule. Greatest thing of right hand 12th standard physics is, yes, the right hand rule, but the 10th standard students, you ask them, they will use left foot rule, left hand Fleming's rule, Fleming's girlfriend's right hand rule, Fleming's girlfriend's mother-in-law's uncle's foot rule. All those rules are there. Okay, but in 12th standard we just have one right hand. Enough, bro, enough. I don't want anybody's hand, anybody's foot and all of that. My one right hand is more than enough. Yeah. Yeah. Online classes like robot? No, I don't feel like robot, man. I love online classes. I love, because I'm not just, I love offline also. It's not like I don't like offline. Offline also had its own fun, but I like online also because I might not see you, but I know what is going on in your mind. I have taught for a lot of time on offline, right? And I keep interacting with students, seminars, so many times I keep going to offline also. So I know what and all you are. Your face will change, but mind is the same. Little bit plus minus is there, delta dx, but that x is same only. It's like a variable. Okay. So that person will keep changing, but I know the mentality. So don't worry. I know you all properly. Okay. Perfect. Now, having said that, the speed of light with the wave equation, we can directly get it looking at the wave equation. But also, if you just divide both of them, you will get it, the electric field and the magnetic field. So if you take the electric field and the magnetic field and you divide both of them, E by B, you will also get the speed of light. So this V has to be equal to the speed of light. So I cannot just leave it as V. So this V has to be the speed of light. So the speed of light is simply electric field magnitude divided by the magnetic field magnitude. As simple as that. Okay, E divided by B. Very, very straightforward. Okay, so these are the equations. Are you now ready for some questions? I have just put it up over here. Okay, all these things, it's one and the same thing. Are you ready for some questions? Yes or no? Let's do it. Okay, here it comes on your screen. There is an electromagnetic wave which is going, oh, this was asked this year, along x direction. The components of the electric field and magnetic field are, okay, so we have our velocity of light c hat, which is going in positive x. That means this will be I cap. So this c hat, I know, will be E cross B, will be E hat cross B hat. Now I cap, what will be I cap, guys? I cap is exactly what? Which direction versus which direction? J and K will be there. So K cross J, J cross K. What is it? Come on. Yes, it will be J cross producted with K hat. Isn't it? J cross producted with K hat. Hi Kuchithila, welcome. So where is J? Y component. Where is K? Z component. Y and your Z. Electric field will be Y, magnetic field will be Z. So electric field's Y component, magnetic field's Z component. That's how simple this question was. Students, teachers complicated it unnecessarily. Not needed. It was very laddu question. Isn't it? Very simple. C hat formula I know. I cap formula, vectors, 11th standard, first, second chapter only. J cross K. It is not K cross J. So compare. E is in J cap, B is in K cap. That's it. There is no other option also which is like that. Okay. Moving on to the next one. There is a plane electromagnetic wave of so many megahertz in x direction. The electric field is this much. What is the magnetic field at that point? Okay, come on guys, what should be the answer for this particular question? Okay, let's try to figure this out. Electric field magnitude is given. What is the magnetic field vector? First, let's figure out magnitude, then let's figure out direction. Magnitude, what formula do we use? Electric field by magnetic field magnitude is the speed of light. So magnetic field will be electric field divided by the speed of light. electric field is 6.3 volt per meter. Speed of light is 3 into 10 to the power 8. 6 by 3, 2, 3 by 3, 1 into 10 to the power negative 8 Tesla. So magnetic field magnitude is 2.1 into 10 to the power negative 8 Tesla. So automatically C option and D option went off. Can you see that, guys? Automatically your C option and D option went off. Okay, now let's talk about the direction. All right, we all know C hat is equal to E hat cross producted with B hat. Okay, speed of light, where is it? It is traveling in X direction. That means this is I cap. Where is electric field? Electric field was given in J cap direction. So if this is J cap, what should be the magnetic field? Come on, guys, this has to be K cap. J cross K will be I. So it has to be K cap. It has to be basically K cap, which means it should be option A. It should be option A. Very good. How many of you got it? Understood? Very good, Vedant Sabrinathan. Amazing, Amara. Very good, very good. The notes will be available after the session is over, man. Right over here. Electromagnetic waves. No, this session is going on. First of all, like this video, guys. What are you guys doing? Go down and you will see right over here. After some time, this description box will get updated. And even in the comments also, it will get pinned. Okay, don't worry. All right, let's move to the next question. This came in 2014, long time back. Long time back this has come. Let's see. For an electromagnetic wave which is going in the Z direction, which of the following combination gives the correct possible direction of electric and magnetic fields? I'll tell you one thing. All those vectors which are perpendicular, only choose them. If something is not perpendicular, ignore it completely. So because that dot product has to be 0, number one. Second thing, if you take E cross product with B, the answer, the outcome has to be Z direction. That means it has to be K cap. It has to be something K cap. So all those options which give me K cap, only they are correct. Other options are wrong. That's it. So if you check the first option, what will it be, guys? What will it be? Check it out. I plus 2j cross I plus 2j cross product with 2i minus j. I into 2i is 0. I into j is k, but with that negative sign, so minus k cap. Then 2j cross 2i will be negative k only, but it will be negative how much? 4k cap. So this will be minus 5k cap. So this is obviously wrong. This is obviously wrong. Okay, this can't be correct because I should get positive k cap. How about this one, B option, guys? Yeah, it's D. Okay, I don't know whether it's D or A. If it is D, then I'm really unlucky because I will be checking 3 options to figure it out. But I cannot blame my luck now. Anyways, let's try to do this. So minus 2i into 3i I cannot do because it will be 0. Minus 2i into minus 2j. Minus minus will cancel. I into j is k. So 2 2s are 4. So it will become 4k cap. Minus 3j into minus 2j is 0. Minus 3j into plus 3i. So negative will be there. But j cross I will make it positive again. And 3 3s are 9. So 9k cap. So that will make it basically 13k cap. Oh, I got k cap. So yes, this is the answer. I don't even have to check others, but I know others will be wrong. You can try it out. I got lucky at least in the second go. Yeah. So I think the answer should be option B, guys. Yes, it is B. Check it out. It is option B. If you try out other things, you will get something else. Yeah. You can check dot product. I will tell you something. For let's say the examiner is smart. All the dot products are 0. Then you are in a soup. You have wasted double time now. Now you have checked all the dot products. Okay, they are all 0. So all of them are perpendicular, but only one of them is getting positive k cap. All are others are giving negative k cap. So you have wasted time in dot product. Now you are again going to check. all the options, and your luck is bad. All the first three options are giving minus k cap. Only the last option is giving plus k cap. So lot of time wasted. So don't do that. Cross product is simple when you have just two terms. Yeah, when there are three terms, I, J, K, then multiplication becomes lengthy. But for two terms, it's just two things which will be there, no? Because I into I is 0, J into J is also 0. Only I into J will come and J into I will come. So two things being multiplied, it is very laddu. That though anyways you will be doing in dot product. AX BX plus AY BY. So might as well do it for cross product now. Getting my point? How you should save time? There is nothing wrong in your method. Maybe your method might suddenly say that, other three vectors are not even perpendicular. Oh, then it will look like, oh, it's a very good thing. But you have to think of other extreme also. What if all of the answers come out to be 0 in the dot product? Then you are in a big soup. It will be a wastage of time. Okay. Moving on to the next question, looks like a big one. Electromagnetic wave. Oh, by the way, just 1 second before going ahead. For example, in this question only, because the wave was going where in z direction, guess how the equation will look like? It will look something like this. E naught sine will be there, but kx won't be there. It will be having kz and minus omega t. Do you understand why z will be there instead of x? Because it is going the z direction. If it was going in x, it will have x. Why? Y. So it is going in z direction, that's why z is there. It's going in positive z, that's why negative sign is there. If it was going in negative z, then this would be positive symbol over here. Okay? Perfect. Awesome. Now, moving on to the next question. Electromagnetic wave in x direction has some frequency, amplitude. From the options given below, which is the correct one for the magnetic field? Oh my God. Yeah, now this is going to take some time. Are you ready for it? Are you ready for it, guys? Sir, isn't option C also plus k cap? I don't know, guys. I mean, just check it out. If it's positive k cap, then multiple options will be correct. But then it would be a mistake in the printing. But mostly the answer was B only. But maybe plus minus sign somewhere they missed out. Otherwise, you now know the method. Okay, you can check it out. Okay, so let's go. Positive x direction is given. So kx minus omega t, kx minus omega t, kx minus omega t, kx minus omega t, kx minus omega t. So this is already being taken care of. Frequency is given, so we can find omega. So omega is 2 pi multiplied by f. So 2 multiplied by 3.14 multiplied by 23 into 10 to the power 14. How much is it coming out to be, guys? 2 3s are 6.28, 6.28 into 23. Come on, how much does it come out to be approximately? Oh, I don't have to do that, is it? Because everything is in pi terms only. Acha, so we don't have to do that. So this will be just 2 pi multiplied by 23 into 10 to the power 14. So that will be just nothing but 46 pi into 10 to the power 14 radian per second. 46 pi. Okay. So 46 pi will be there, or basically we'll just put 23 over there. That's it. So 2 is there, 2 is there, 2 is there. Is there some mistake in the printing somewhere? Because if it is 23, then all the options are going wrong. If you see 2 is there over here, omega t, 2. I think either that 3 was not there, or maybe, 23 was there. Yeah, 2 pi is taken common, yes, correct. But I have a feeling that I think there is a printing mistake somewhere. I'm sorry, I'll have to look at the solution because I think there is some printing mistake. Omega is 2 pi f. Yeah, see, I figured it out. There is a printing mistake. They have taken 2 into 10 to the power 14. So that number 3 was not supposed to be there. Okay, fair enough. So sometimes printing mistakes also cause unnecessary issues. So just 2 pi multiplied by 2 into 10 to the power 14 radian per second. So I can see 2 into 10 to the power 14, 2 into 10 to the power 14, 2 into 10 to the power 14. Oh, this is also taken care of. All the options are correct. Electric field is given, magnetic field is asked. You can see K value is also, I think, no, only in two options it is same. Other two options it's different. We can find the value of K. How? We know omega by K is speed of light. That means K value will be omega by C. So it will be 2 pi multiplied by 2 into 10 to the power 4 divided by speed of light, which is 3 into 10 to the power 8, which will give me 2 pi multiplied by 2 by 3, isn't it? I'll have 2 by 3 over there. Just check this out. K will be omega by C. Perfect. Nothing wrong over there. Yes, this is 2. C will come down. So 2 by 3, that's nothing but 0.67 or 0.66 recurring, and 10 to the power minus 4. Just check this out. So 10 to the power minus 4. But again, I'm seeing printing mistake everywhere. Wow, looks like this question has a lot of printing mistakes. I'll have to go look at the solution. Yeah, see, here also, same thing, what I got, 0.67 into 10 to the power something. So guys, definitely, there were issues. There were issues over here. Oh, this was 10 to the power 14, my bad. This was 10 to the power 14. So forget the options, guys. Forget the options over here. Yeah, this was 0.67 into 10 to the power minus 6 radian per meter. The options are not matching. We have no other choice but to forget the options and just do it normally, because options are not matching. So no point looking at it. Okay, now let's look at the magnetic field. Let's look at the magnetic field. How do I find the magnetic field from electric field? See, electric field by magnetic field is speed of light. That means magnetic field amplitude will be electric field amplitude divided by C. Electric field amplitude is 27 and speed of light is 3 into 10 to the power 8. 27 by 3 is 9. So 9 into 10 to the power minus 8. This will be Tesla. At least that much part was fine. Okay. So from this, we can guess what the magnetic field wave equation will look like. It will have magnetic field, it will have sign, then it will have kx because it is going in the x direction, but positive x means negative sign, and then omega t. So b naught will be there, which is 9 into 10 to the power minus 8. Sign will be there. K value will be also there, which is 2 pi, and k is nothing but 0.67. But 2 pi will also be there over here, 2 pi into, okay, so 2 pi into 0.67 into 10 to the power minus 6 minus omega. Omega is this, 2 pi is already multiplied, so 2 into 10 to the power 14t. This will be in Tesla. That will be your wave equation. Magnetic field wave equation. This is how it will look like. K value I have put, omega value also I have put. K and omega both had 2 pi in common, so I've taken the 2 pi outside. If you ask me direction of this wave, one thing is that it will not be I cap for sure, but electric field amplitude is not given direction wise. So there is only one possibility now. Think like this. The speed of light is E cross B, right? This is I cap. So I cap will be definitely J cap cross K cap. J cap cross K cap. So magnetic field will most likely be in K cap direction. So if at all I had to mark something, I'll put K cap, and rest everything will be as it is. Yeah, that's all. So this will be the magnetic field vector. Magnetic field vector. Is that clear, everyone? Perfecto. How do we solve this kind of questions? Yeah, they are also very common, guys. Okay, so you should know about this. The options did not match because some printing mistake is there definitely over here. So no point checking the answer also. Anyways, let's do the next question coming up on your screen. The electric field is given by this equation. The magnetic field will look like how? Electric field is given 59 cos something t minus something 3x plus 4y and 4 I cap minus 3j cap and God knows what and all. So now this was a very good question actually, which was asked this year. This was a very, very good question actually, which was asked this year. And many students, they didn't figure out how exactly to do this. Okay. Are you ready to do this particular question, my dear students? Yep. Ready for it? Awesome. Let's do it. First of all, if omega is over here, the same omega should be there everywhere. So omega t, omega t, omega t, omega t. See, omega wise, it is perfectly balanced. I mean, all options are looking okay. There is nothing wrong over there. K value is basically this over here. So 5 into 10 to the power minus 3, minus 3, minus 3, everywhere it is the same thing. So I cannot even choose anything over there. There is a minus sign, minus, 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 that is also done. Okay. Now, the only thing which I can take care of is the outside part, which is this one. This is the amplitude part. This is the amplitude. Do you know there are some anomalies? It is looking slightly different. Usually, inside K, there should be X or Y or Z, but there is 3X plus 4Y, number one. Number two, outside either it should be I cap or J cap. This is 4 I cap minus 3 J cap. So these are the two weird things in this equation, which I will talk about. Hold on. So how do we take care of X and Y together, I and J together outside? So is really 57 the amplitude? The answer is 57 is not really the amplitude of this, because 4 I cap and 3 J cap, they as a vector quantity is not a unit vector. So technically I should not take 57 as my amplitude. That is a mistake. Okay, a lot of students do that. They take 57 as their amplitude, but that is definitely wrong. So what actually you should be doing? I'll tell you. This particular equation which is there for electric field, where is it? E is equal to 57 4 I cap minus 3 J cap. 4 I cap minus 3 J cap. Then you also have cos instead of sine, and this whole thing. For now, I'll just put omega t minus k. I don't want to write down this entire thing. 3x plus 4y. 3x plus 4y. And this was Newton per Coulomb, because this was electric field. This was in vector form. Okay, this is the equation that I'm getting. Everybody till this point absolutely clear? Instead of values, I have put omega and k. Okay, rest everything is as it is. This 4i minus 3j, I've just put it after 57. Now I'll tell you what we can do. Let's write it down in unit vector form. I'll tell you how. This will be 57. The magnitude of this vector is 5. 4 square plus 3 square is 25. So root of 25 is 5. So make it into a unit vector. I'll tell you how. 4 I cap minus 3 j cap divided by its magnitude, which is 5, to preserve the equality, multiplied by 5. Now this particular vector itself is a unit vector. So this is basically the unit vector of electric field, and then you have this cos term and whatever is there over here as it is. I'm not touching that. What is this quantity telling me? This quantity is telling me in which direction is the electric field. This is the unit vector of electric field. This then becomes our E naught. You are asking me, right? What is E naught? This is basically E naught. Okay? Everyone fine till this point? Okay. From this, now we can find B naught. How much will be B naught? Well, for that, Electric field amplitude by magnetic field amplitude is speed of light. So therefore, magnetic field amplitude will be electric field amplitude by speed of light. So electric field amplitude is 57 into 5. Speed of light is basically your 3 into 10 to the power 8. Okay. Hence, if I had to write magnetic field equation in vector form, I will be writing 57 multiplied by 5 divided by 3 into 10 to the power 8 with the unit vector b hat. With the unit vector b hat, like this one, there will be a b hat, which I do not know what it is. For now, just leaving it like that. And next will be basically your cos and all those terms. Omega t minus whatever that k into 3x plus 4y bracket complete, but in Tesla. This is how the equation will look like. Is this absolutely clear, everyone? How many of you got this understanding till now? Hakka? Okay, cool. Yeah, awesome, awesome. Okay, great. Now our job is not yet done. The problem is I do not know what is b hat. Okay, that is the problem. So I'll tell you what. To find out b hat, you will be like, sir, we know what to do. What to do means get rid of this. Sir, we just have to take c hat is equal to E cross B. Okay, correct. You are right. Absolutely. E hat, I already know. E hat, I already know. It is basically your 4 I cap minus 3 j cap divided by 5. The problem is, how the hell am I going to find B hat when I don't even know what C hat is? Sir, don't we know C hat? We do not know C hat, man, because it's not just in X, it's also in Y. It's going in XY plane. See, this is X axis, and let's say this is Y axis, this is Z axis. The wave is not going here. The wave is not even going here. The wave is going here. That is the problem. The wave is going in some XY plane, some random direction, which is given by that. Oh, this is the problem. That's what many people don't even understand. So you cannot use this, number one. Number two, let's say we find C hat and we know E hat. Even then, I cannot use this equation to find so easily B hat. Rather, recollect when we had to find B hat, going back. If I have to find B hat from C and E, I will use this. B is C cross E. B is C cross producted with E. So my B hat vector will be C hat cross producted with E hat, where E hat is 4 I cap minus 3 j cap whole thing divided by 5. Okay. So now, how do I know what C hat is? Because once I know C hat, only I can get B hat. And once I know B hat, only then I can substitute it back here to get my full equation. Okay, let's think. Here, this term, whenever it is there, how you should look at it means this kind of equations, whenever it is in 2 dimension or 3 dimension, the generalized wave equation. So a wave in 3-dimensional space will look something like this. Electric field will be, vector will be E naught, and then you will have sine or cos, it doesn't matter. You will have omega t plus or minus, doesn't matter. You will have k into something. I'll tell you what that something is. But here you will have an unit vector E naught cap, which is the same like this one. E naught cap is like this one over here, which is the unit vector along which the wave is moving in some random three-dimensional space. This is your random three-dimensional space that particular wave is going, okay? Somewhere it is going, I do not know where. And inside over here, this is the tricky part. It is k bar dot r hat, or basically c hat. K bar dot c hat. This is the modified equation for a wave in three dimension. There is a dot product with k and c. Basically, that's what it is. Okay, or just you can forget that dot product, just put kc hat for now. Just put kc hat. Okay, just put kc hat magnitude over there. So that 3x plus 4y is basically the direction in which the light wave is going. So the answer for this is 3x plus 4y is the directional vector. So C bar is 3i cap plus 4j cap. So C hat will be 3i cap plus 4j cap, whole thing divided by 5. So whatever that is there, that is the directional vector in a way for velocity of light. So put that over here. So 3i cap plus 4j cap, whole thing divided by 5. Now you do the multiplication and see what b cap will be. By the way, 5 into 5, we already can see it. It will be 25 in the denominator. 3i into 4i, 0. 4j into 3j, also 0. 3i into 3j. I into j is k, but with a negative sign. 3 3s are 9, so minus 9k. 4j into 4i. J into I is negative k. 4 into 4, 16, so plus 16k cap. Sorry, negative k will be there, my bad. Negative 16k cap. Okay, so this will become minus 25k cap by 25. Is that right? Just check this out. 25k cap by 25. 5 will cancel. So 25 by 25 will be 1. So it will just become minus k cap. It will just become minus k cap. How many of you got it now? Understood? Clearo? Perfecto? Very good. This is very, very important, guys. How we are using a modified equation. We are not using C is E cross B. We are rather using B is C cross E. That will be more beneficial for us. C hat, I got it from here. E hat is basically your this unit vector. And this is from there, I get the value of B hat. Once I know B hat, I can just substitute it over here. So this will just become 57 multiplied by 5 divided by 3 into 10 to the power 8, and then you have cos, and then that omega value, whatever it was, where is it? 7.5 into 10 to the power 6, 7.5 into 10 to the power 6 into t minus k value, whatever it was, 5 into 10 to the power minus 3, 5 into 10 to the power minus 3, then 3x plus 4y, bracket complete, and b hat was negative k cap. This was negative k cap, so I'm just going to put a minus sign over here. So this minus sign is taking care of it. Okay, where is that? Minus sign is there over here. So I'm just putting it as it is over here. Negative k cap Tesla. So that is your magnetic field equation. Got it, guys? How to do it? Oh, welcome Techno to the intermediate level. It was a beautiful question. Okay. So what will you do in the exam? Will you do all this step? It is very nice to see all this, very nice for a concept. But in the exam, if I was writing that exam, even if I would be training the toppers batch, I will tell that person, please leave that question, keep it at the end. There are other good things to be done. Yes or no? Will you do it in the exam? You are definitely not going to do this in the examination. So These kind of questions always brainwash the kids. They, sometimes tell the kids, oh, this kind of question also came. But one question will be like that. All questions won't be like that in the exam. Okay. So you have to have that courage to leave it and do something else. Else you are wasting your time. You have taken it personally on your ego. You have taken it on your ego. No, I have to be a hero person. I have to solve it and all of that. You cannot do it. Yeah, definitely. Very good. The magnetic field of an electromagnetic wave is given by blah, 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 blah. The corresponding electric field. From magnetic field, you have to find electric field. Guys, similar question, guys. So Z is there. Z has to be there. But minus is there. So check this out. There is a minus sign here. The minus sign is only there over here and over here. So this option can't be correct. Even this option can't be correct. Either it has to be this or this. Okay. B or D. There is sine over here. So it has to be sine. There is cos. There is sine. Can you see that? That's the next problem. Sine is there over here. Sine is there over here. There is cos over here. So this can't be correct. So obviously only option B is the right answer. So this can be solved within 20 seconds if you think about it. You don't have to sit and solve it properly because you just had to eliminate options. This kind of questions are very, very doable and you should do it within 20-30 seconds. But if at all you could not eliminate it, then how would you do it? See guys, again, this is a vector over here. Do you notice this is actually a unit vector? How many of you noticed this is actually a unit magnetic field vector? Unit magnetic field vector B naught cap. This is unit magnetic field vector. And the speed of light, c hat, it's going in the z direction. But since there is a minus sign, it is going in the positive z. So c hat is basically k hat. So B naught, you just have to find E hat now. What is the formula for E cap? What is the formula for E cap? Just going back to our theory page again, where we did it. Yes. E cap is B cross C. E cap is B cross C. That's E cap is B cross C. So just going to put B cross C. Solve this. You are going to get solving this cross this, which is root 3 by 2 I cap plus 1 by 2 j cap cross producted with k cap. That will give me the value of E cap as exactly half I cap minus root 3 by 2 j cap. So that's it. So that is exactly right over here, which is the unit electric field vector. So this is unit electric field vector and your job is done. Okay, that's how you're going to solve it. Is that clear, everyone? Okay, amazing. Now let's go to the last few things. Speed of the electromagnetic wave. Guys, we are just going to be done within 45 minutes. Okay, not more than that. So I will not be giving a break because again that momentum, that flow will go. 45 minutes we are done. I'm telling you, not much is left. Speed of a electromagnetic wave, we already saw V is omega by k or E by B. But if I don't know electric field, magnetic field, or if I don't know the wave equation, how do you get the wave speed? Then the answer is through the medium's properties. So it so happens that the wave speed in general is 1 by root of permeability into permittivity. That's it. But if the medium changes, so the speed in different medium, this is in vacuum, you can use this. This is permeability and permittivity of vacuum. So the only change will be permeability will be written down as permeability into relative permeability. This will be permittivity into relative permittivity. That's it. That's the only difference. If you want, you can rearrange this a little bit. Like take mu naught and epsilon naught together. So take permeability and permittivity in together, and then these two will be together for relative permeability and relative permittivity. But this quantity is the speed of light. So technically, this will be speed of light in vacuum divided by the relative permittivity and relative permeability. That's all. Right. That's it. So this is how you can write it down as. So this is a formula which you should definitely know. This is for vacuum. Okay. Very simple and sweet looking formula. From this, you can even find refractive index, because if you know the speed of light in both the medium, the division of the speeds gives me the refractive index. So those kind of questions also come. Same thing has been put over here. Speed of light is 1 by root mu naught epsilon naught for electromagnetic waves. So it depends on the permittivity and permeability properties of that medium. Okay. So let's do some questions so that you guys get an idea of it. Refractive index, if relative permeability is 2, relative, oh, susceptibility is 7. Susceptibility, guys, is X. So from that, relative permeability, which is 1 plus susceptibility, so 1 plus 7, which means it is 8. So indirect. Can you hear me now? Can you hear me now? Yeah, the battery went off. Okay. But I think you understood this question. This was speed of light is c by 4. So in general, refractive index is given by medium's speed is vacuum speed divided by mu. So if you compare both of them, mu will be 4. Okay. NCRT line by line, I have already done it last year, man. So you can watch the same lectures. It's not going to be different because same NCRT is used. So use the same old classes. Okay. Critical angle, diamagnetic medium, relative permeability, 0.5 is 30. Well, critical angle formula is from ray optics. Sine of critical angle is 1 by refractive index. So sine of 30 degrees is 1 by mu. Sine 30 is half. So therefore, my refractive index is basically 2. Now from this, I will think. See guys, speed of light in vacuum was speed of light, sorry, speed of light in medium is speed of light in vacuum divided by relative permeability into relative permittivity. Now, if you take this guy on the top, it will become like this. Relative permeability into relative permittivity is C divided by V. This quantity C by V is actually the refractive index. Is basically our refractive index. Okay, so here we will have root mu r into epsilon r. So now relative permeability is given to be 0.5. Okay, multiplied by permittivity, I do not know. Refractive index, we just got it as 2. So square both sides. Square both sides. So you will get 0.5 multiplied by ER is 2 square. So relative permittivity is 4 divided by 0.5. So this will be basically 8. So relative permittivity is nothing but 8, guys. That is the answer. Simple. Understood how to solve these kind of questions. So these straightforward questions can also come in your examination. Now let's go to last couple of things, energy density and electromagnetic spectrum. Two small things are remaining. So let's go to that. The energy of light is there in both electric and magnetic fields. The energy of light is there in both electric and magnetic fields. So the energy of a light is in electric and magnetic fields, but it is also distributed equally. Light will not bias towards electricity or magnetism. It distributes the energy in equal terms. The energy of light is distributed equally in both electric and magnetic fields. In both electric as well as in the magnetic fields. That is number one. So I can definitely say the energy of a wave, electromagnetic wave, is 2 times electrical energy or 2 times magnetic energy. One and the same thing. Okay. So let's find out how much is that energy. So for that, if you just consider, for example, electric wave, okay, if you just consider electric wave, the energy per unit volume, the electric energy which is there per unit volume, let's calculate, which is also known as electrical energy density. It has a formula, try and recollect, half epsilon naught E at that moment square. Half epsilon naught E square. This formula I've studied in electrostatics capacitors. But the problem is the electric field is continuously changing, sometimes less, sometimes more. So this is also going to vary. So this is very, very critical for you to understand. Since this will keep changing, this will keep changing with our time. So even this energy per unit volume changes with time. But I don't not interested in the changing value, because what will I do at this time, what is it at the other time? Rather, I want on an average what is the value. So what I will need is the average value of this is the symbol for average. So half epsilon naught average of the electric field square. This is what I will need. Okay, I will need basically average of the square of the electric field. This quantity, I know what it is called. So whenever you have a sine cosine function, it is changing, you want to find the average of the squares. That average of the squares, mean of the squares, guys, RMS value. Exactly, if you thought about it. So this should be nothing but the RMS value square. RMS square value, because there is a square over there. So the square, the mean of the squares is the RMS square. How many of you got this? Because root mean square means the root of the mean of the squares. So I'm not taking root. That's all. It should be just the mean of the squares value. So what is the RMS value of a sine function. The RMS value of a sine function is nothing but the peak value like E naught divided by root 2. Divided by root 2. Okay, so root 2 square is 2, 2 2s are 4. So this will become 1 by 4 epsilon naught E naught square. That is the average electrical energy density. That is the average electrical energy density. Is that absolutely clear in your head, my dear students? Everybody? Okay, this is how the derivation happens. The same logic one can also apply for magnetic energy per unit volume. For magnetic energy which will be present in that wave per unit volume, joules per meter cube. So it will be density of the magnetic field which will be changing. It will be half magnetic field square divided by mu naught. But not to mention, this will be a function of time. So this will also depend on the value of the time that you are taking. So if one decides to take the average value of the magnetic energy, I will have to take half mu naught separate and I have to take half average of the B square value, which is half mu naught magnetic field RMS square, which is nothing but B naught magnetic field amplitude by root 2. So this is going to give me 1 by 4 and B naught square by mu naught. So that is the average magnetic energy density. Average magnetic energy density. Is that clear, everyone? So now if I want to find the total energy which is distributed equally basically, so the total energy density, so the total energy per unit volume, which I will just call it rho, will be nothing but the density of electric field plus the density of magnetic field. We can also write it as 2 times, we can also write it as 2 times density of electric field energy or 2 times density of magnetic field energy. Why were we able to write this? Since they both are equal. Who are equal? Electrical energy density and magnetical energy density both are equal. That is what I told you initially. They are equally distributed. They are equally distributed in both electric and magnetic fields. So they both are equal. So I just have to multiply the number 2. So if I use the electrical formula, then the field will look, sorry, energy per unit volume will look like this. So 2 times of this. So 2 times of this or 2 times of other thing. So 2 times of 1 by 4 epsilon naught E naught square, or we can use 2 times of 1 by 4 B naught square by mu naught. Either ways, what will we get? The energy density will be 2 and 2 will cancel. So it will become half epsilon naught E naught square, which is also half B naught square by mu naught. Both formulas are correct. There is nothing wrong in using any one of them. Both are fine. This is very, very important. So half epsilon naught E square, but that E is electric field amplitude. Half B square by mu naught, but that B is magnetic field amplitude. So if you know this and understand it, it is more than enough. So this derivation, I feel, is very critical for understanding a lot of things. RMS, how the averages work and how it comes. Else many people make a mistake in that number 2. Where is it 4? Where is it half? You'll get confused. So if you know the derivation, I feel now you'll never be confused. Okay, very good. Now this energy density is also related to its volume. We'll come to that, but before that, I think we have a question on numerical values. Okay, first we'll do that. Electromagnetic wave of so frequency, amplitude this much, epsilon naught this much, the average energy density of the electric field is asked. Only the electric field's energy density is asked, guys, not the entire waves. So you need to be careful in choosing which formula you are going to stick to. Think logically. Yeah, only electrical energy density is asked. So that means you'll be using 1/4 epsilon naught E naught square, not half, because only electric field density average is asked. That average is asked. So 1/4 into permittivity is 8.85, 10 to the power minus 12. Electric field is 4, so 4 square. So 4 will cancel. So 4 into basically 8.85 into 10 to the power minus 12. So 8 fours are 32. So it will be more than 32. So it will be around 35.2. Yeah, that's what it should be. So 35.2 into 10 to the power minus 12 joules per meter cube. Where is it, my dear students? Yep, option number C. Option number C is the right answer. Clear? How do we do this? Very direct kind of questions are there. All right. Moving on. Moving on now to another question. Moving on now to another question. This is also a very nice question. Let's see. This was asked this year. Due to an electric field, electromagnetic wave, the electric field is this, and it is inside a cylindrical area of length 200 centimeters and holds that electromagnetic wave energy. So you'll have to visualize this. Imagine there is a cylinder, and in that cylinder, you have that electromagnetic wave, and it is filled with it. It is moving. So you are just considering a small part of a big electromagnetic wave. So in that cylinder, that energy which is there is given to be same as the other electromagnetic waves energy. So there is another cylinder of same length but half the diameter and holds the same electromagnetic energy, then how much electric field is there in the other cylinder. So basically there are two cylinders which are being compared. Let's try to understand how do we do this particular question. It's a very interesting question. Try to read it again. What and all is same, what and all is different. Okay. Now, let's say if you just concentrate, you can take any electrical or magnetic energy, but let's just take the total energy, which will be the same in both of them. So the total energy density in both of them or any one of them is given by half epsilon naught E naught square. Energy density means the total energy, so I will call it as U, for example, divided by the volume, I'll call it V, divided by half epsilon naught E naught square. So therefore, my energy will be half epsilon naught E naught square. What is this volume? It is area multiplied by length. And now let's write down the formula for area, because the question is on diameter, I think. So area of a cylinder, the curved, not the curved, the flat surface area, will be pi into diameter square divided by 4 and into the length. So this is what the energy will be. This is what the energy will look like. Area is pi d square by 4. This is that circular area, length of the cylinder. Okay. Now, why did I write it like this? See, I'll tell you. Energy is given to be the same amount of energy. Epsilon naught is a constant, 2 is a constant, electric field is not a constant, pi is a constant, 4 is a constant, diameter is different, same length is also given. Same length is also given. So the only thing which is different is E naught and D. So from this, we can easily conclude that E naught square, D square is same. But why do we square it? Therefore, I can just say, taking square root, E naught into D is basically the same. So in the first situation, the electric field was 100 amplitude wise. The diameter was d, let's say. In the second case, I do not know the amplitude, but the diameter is given to be half. So it is d by 2. So therefore, my E naught value will be 2 times of 100. So it should be 200. So E naught should be 200. So 200 is only there in this option. Which option? C option. Hence, option C is the right answer. Can you see that? This is basically your E naught. So this was a very good question which was asked this year. But it is completely formula based, but you have to apply your mind. Analytical skills will matter. But if you know the formula, it will help you. But just knowing the formula also doesn't help, because you have to think, oh, cylinder is given, energy will be distributed. So we know energy per unit volume. So I can find the volume of the cylinder and then I will get total energy. And that total energy was given to be the same. So then I can compare and I can get some relation. Yeah, it was good level of question. Very good. Now, also, intensity is related to the energy density, and I will tell you the formula for that as well. Remember, in general, intensity of light is nothing but how much energy is flowing per unit time, per unit area. That is what intensity was, and the unit was nothing but watt per meter square, right? That is what the definition of intensity actually was. And if you take a point source, so for a point source of power P, let's say P is the power, the intensity will be energy per unit time which is being generated is P, because P is in watts. Area which will be there, it will be 4 pi r square, because the point source will give the energy in the big sphere, and the sphere will keep changing its size as the light moves. So P by 4 pi square will be the intensity of that light due to a point source. This is how you can think about it. Now, how is this intensity related to our energy density? Okay, there is a logic for it. See, I'll tell you one thing. Our energy density which was there, on an average, that was how much energy is there per unit volume, isn't it? The energy per unit volume. Intensity formula which is there, it is energy per unit time per unit area. I can see energy is same in both of them, U. So somehow I need to get rid of that U variable somehow. Let's think, how can we do it? So I have an idea. Instead of writing this as U by volume, I'll write it as area into the length. Interesting. Now, what do I do with this? Here is what I will do. Check this out. From here, U divided by A, if I do it, that T which is there below will go on the top. So it will become I multiplied by T. So instead of U by A, why not put it as intensity multiplied by time? Rest of the terms is as it is, like length. So that will give me energy density. Now I have an idea over here. I'll write intensity as it is, this length as it is, and this time I will take it below deliberately. Why did I do it? Length per unit time, the length that I'm traveling in that time interval is the speed of light actually. So it will become intensity by speed of light, that is energy density. So intensity in general, so this particular intensity which was there will become rho C. Very important formula. Intensity will become energy density multiplied by the speed of light. Very, very important. Okay. So if you know energy density, multiplied by the speed of light, you get the intensity. Very straightforward. Okay, perfect. Let's do this particular question. This was asked. The unit of root 2I by epsilon naught C is how much? This year again on electromagnetic waves. Believe me, this is not just a question on units and dimensions, but also on electromagnetic waves. People did not realize it. How? Check it out. We all know intensity, just now we studied this, is rho C. Intensity is rho C. What is energy density? Half epsilon naught electric field square into C. Okay. So looking at that, I got this idea that maybe it is related to electric field concept. So I'll rearrange it. So take 2 on the top, take I on the top only, it is there. Take epsilon naught and C below. Take epsilon naught and C below. What will be left is E naught square. So therefore, E naught will be root of 2I divided by epsilon naught into C. So what is this quantity essentially? This quantity is nothing but electric field. Electric field. And what is the unit of electric field? Either you use Newton per coulomb or you use volt per meter. So I think Newton per coulomb is there. Hence B option is the right answer. So see how they ask these kind of questions in JEE. They couple it with some random chapter sometimes. Okay. Is that clear? Thermal properties already have done. Just check the JEE booster, mini series which we had done after your Diwali. I had done thermal properties. Just scroll below, you will see thermal physics, thermal expansion, and all that. JEE booster. Just in the month of November, say on. And you can also check my very old classes also. Okay. And the last thing that we need to do is electromagnetic spectrum. Okay, ready for it, everyone? All right, let's do this. So, oh, by the way, there can be these kind of questions also on this formula, which I just did. Like, for example, I will not solve it, but I'll tell you. They can tell you, listen, bro, there is a source of some, I don't know, 100 watts. 100-watt bulb is there. Okay. And it is emitting light, obviously, in all the directions. And, you are going like that, let's say at a distance of 2 meters over here. At this point, there will be an electric field. There will be an electric field which will be there. So question will be, what is the electric field amplitude at this place? So these kind of questions are also possible in the JEE Mains examination. So in that case, what you need to do is to find the electric field, we'll need the intensity. If you know the intensity, our job is done. So how do we find intensity? I just told you, whenever you have a point source, what do you do? Whenever you have a point source, the intensity is P by 4 pi r square. So just use that formula first. Intensity is power divided by surface area of an imaginary sphere. So power, and 4 pi r square, we can find it out. Okay, just keep it on the side. But also, we know intensity, is half epsilon naught E naught square. So these two have to be equated, that's all. So half epsilon naught E naught square will be equal to power divided by 4 pi r square. So start shifting the things. You will see E naught square is equal to, okay, P will be there on the top as it is. 4 and 2 will cancel, it will become 2 into pi. R square will be there as it is. Epsilon naught will come below. That's it. So therefore, E naught will be root of power. If you want to take the radius outside, so root of power divided by 2 pi into epsilon naught. So now you just have to substitute. Distance is 2. power is 100, pi value you can put 3.14, and permittivity will be 8.85 into 10 to the power minus 12. So solving this, you will get the answer of electric field in volts per meter. So this is also a very common type of question, calculation wise, which you can get. But did you understand the concept behind it? Intensity for a point source formula. Intensity in general for an electromagnetic wave is half epsilon naught E naught square, direct. You can use it. Okay? Yeah, perfect. So solving this, you will get the answer. Okay, so this was very important. Okay, now the last part, like I was saying, electromagnetic spectrum. This is theoretical part. There is no formula in this. I told you what the humans can see is a very small range of wavelengths. Wavelengths can go from kilometers to millimeters to angstroms to femtometers, but not all of them are perceived by humans. Some wavelengths are perceived by bats, some wavelengths are seen by dogs, some wavelengths are seen by snakes. Sometimes there are overlaps, sometimes there are no overlaps. If you have overlaps, that means the dogs can see whatever you are seeing, plus they are seeing something what you can't see, and you are seeing something which the dogs can't see. But if there is no overlap of wavelengths, then that would mean that animal will not be able to see exactly what you are seeing, but it will be seeing some different colors, and you are not able to see what the dog is seeing. So, you know, uh, we see a very small spectrum or a small part of the entire spectrum, I would say, that is called as a visible spectrum. So on this line, we start plotting frequencies and wavelengths. Here, the wavelengths are small, but the frequency is large. Here, the wavelength is large and the frequency is less. So the largest wavelength in the visible spectrum, this is a very small range. The largest wavelength is basically 700 angstrom or 700 nanometer or 7000 angstrom. So this is the largest wavelength which we can see, 700 nanometer, which is 7000 angstrom. Beyond that, you have infrared. The wavelength is even larger, and infrared rays go beyond 700 nanometers to something like 1000 nanometers, 1200 nanometers also. If you increase the wavelength even further, you go to microwave range where the wavelength is in few millimeters or micrometers. Okay, you go to few millimeters range. If you increase the wavelength further, you go to something called as short radio waves, where the wavelength is in centimeters to meters. And if you increase the wavelength even further, then you go to long radio waves, where the wavelength is in kilometers. Huge wavelength. Where do you use such huge wavelengths? For long distance communication with satellites or with some Mars rover or something like that. Very far away communication, the wavelength is so huge that easily it can be transmitted, and that's the usage of it. Short radio waves are used in your normal radio, ham radio, or that FM AM radio. Nowadays you don't use it, but those radio frequencies, or even when the pilot is talking with the control tower, the ship captain is talking to the lighthouse or whatever. So they use short radio waves for communication, but over long distances on Earth or for broadcasting. Message has to be broadcasted. They use generally short radio waves. Microwave is used in microwaves, the microwave oven, because the frequency which you get for millimeters wavelength is very close to the frequency of oscillation of water molecules, meaning their natural frequency. And it so happens that there is a phenomenon called resonance, where if your frequency is being touched upon and you are oscillated with your natural frequency, you begin to vibrate very vigorously and your oscillation amplitude is very large. So everything in this universe has its frequency. And if you tune into that frequency or you push that body into vibrations into that particular frequency, not any other frequency, then the body vibrates with a large amplitude. So using microwave on water molecules makes the water molecules vibrate due to resonance. And when the water molecules vibrate, then they will have thermal energy, so kinetic energy. So they will become hot, and that's how the other things in the microwave become hot. But ceramic or other things, glass, they do not oscillate because of microwaves. So that is why inside a microwave oven, only the food which has water molecules or close to the frequency of microwaves will become hot. Other things will become or will not become hot. They'll just remain as it is. So that's a very fantastic thing which humans have discovered, that food particles resonate, whereas the rest of the plastic bowls or ceramic bowls, they stay almost as it is. Okay. Infrared rays are used for thermal imaging. Right now, I am emitting infrared rays. Unfortunately, you cannot see it because it is beyond the visible range. But some snakes and some reptiles can see that infrared rays. So that's why even when it is pitch dark, if you are thinking you can be safe from a snake, then trust me, you cannot, because the snake can still see you, because the body heat is emitting infrared electromagnetic radiation. I know you are already scared of snakes, but this one thing has added to one more list of the fears. So most of the reptiles can see you even when you are in the dark. That's why you might have seen military people, they use thermal imaging goggles and vision, where the cameras capture the infrared rays and they convert it into a false color, because still you cannot see infrared. So the image processors and the computers inside, they convert it into false colors and they make you see like white or green or blue or like that. So that's the purpose of thermal imaging. Infrared rays are also used to detect if a person has fever. During COVID times, you might have seen that the security guard used to hold one scanner, and on that the temperature used to come. That works exactly on infrared rays. If you are having fever, you will be hot. That means more amount of infrared range will be emitted by you, and that is what is detected by the thermal imaging sensor. So that tells whether you have fever or not. Okay, interesting. Okay, visible range, so we don't have to talk about it. I mean, you all know. The smallest wavelength is of violet, which is of 400 nanometers. The average color is yellow, okay, somewhere in between of a red and violet, somewhere in between. And rest all are violet, indigo, blue, green, yellow, orange, red, and their combinations. Okay, let's not talk about that so much. That's not important. Let's go to ultraviolet. Ultraviolet is of smaller wavelength, less than 400 nanometers. So few nanometers, 2, 3 nanometers, 10 nanometers will be ultraviolet range. Now, you might also remember from the chapter of atomic structure that ultraviolet range comes from Lyman series. Then you go to Balmer series, which goes to uh, visible range. And then you go to Paschen and Pfund bracket, they go to infrared range. Okay. So ultraviolet comes from that Lyman series of hydrogen spectra, number one. Number two, ultraviolet rays can be used as a disinfectant. Is again, during COVID times, you might have seen whatever things you want to carry outside, they used to place it in one box which had UV rays entering it, because UV rays are very harmful and they can damage bacteria and viruses and all of that. So it's used like a disinfectant, number one. Also, UV rays are harmful for us, so long exposure can cause damage to our skin. So that's why we use sunscreen with UV protection. So you might have seen those nice, beautiful models. They wear that sunscreen. Shreyas Sir is not looking that beautiful, but okay, just imagine, guys. Okay, so ultraviolet rays are harmful for your skin. They can cause long-term damages, including cancer. X-rays are even shorter wavelength, very high frequency, very energetic, typically in couple of Armstrongs, 0.1 Armstrong, 0.01 Armstrong, that is X-ray, and they can even pass through your flesh. UV rays will not pass through your flesh, but X-rays can pass through your flesh, but X-rays get blocked by our bones, calcium which is there. So that is how we use it to see if there is a fracture in our skull or our bone or in our leg, wherever. So it is used to detect fractures. Very energetic. They can even ionize the gas through which they will pass. X-rays are also used to detect cracks and detect some small holes and gaps in big buildings or even bridges. So it's used for routine maintenance and checkup purposes. Gamma rays, they are even smaller in wavelength, more energetic. Their wavelength is in order of 10 to the power minus 15 meters, which is femtometer. They generally originate from nucleus due to nuclear reactions. And if you have seen the movies of nuclear waste or nuclear disasters like Fukushima or even the Chernobyl movie, which was there on Netflix long time back, so you would know the dangers of gamma rays. It's invisible. You cannot see it, obviously. None of them you can see it except for visible. And even small time exposed person will face a lot of difficulties, and within couple of hours or days, depending on the exposure, the person will die. And if you do not die, that life is even more crazy, because a lot of mutations, a lot of unnecessary complications happen because we cannot sustain gamma rays even for a little bit. Okay, very dangerous, very harmful. Generally from nuclear reactions you are going to see these gamma rays. They also come from outside the solar system due to solar winds and cosmic radiation and all of that. So a lot of gamma rays do come, but it gets absorbed by the time it reaches over here due to the atmosphere and Earth's magnetic fields. So you should know the usage, the wavelengths, the frequency, and the applications. That table is given in NCERT. So please go through that table, okay, properly. I have put it up for you. All right. And the kind of questions which usually come are very straightforward, like the one over here. Like, the following wavelengths are given for the rays. Which of them is largest? Which of them is smallest? Arrange them in order. Very simple. So microwave, X-ray, infrared, gamma, ultraviolet, radio, and visible. Arrange in ascending order. That means smallest first. So out of all of this, obviously gamma rays is the smallest, then X-rays, then ultraviolet, then yeah, correct. So first is gamma rays, then is X-rays, then is ultraviolet, then you will have visible, then you will have infrared, and then you will have microwaves. That's it. That's the answer. Perfect. This is what it should be. Okay. Perfect. See, G stands for what? Gamma. Then X for X-rays, U for ultraviolet, V for visible, I for infrared, M for, what is it? Microwaves, correct? And R for, what was it? Radio waves. So radio waves will be the last. Yeah, perfect. Yeah. So these kind of questions are there. Then again, this kind of questions. Match the following. Approximately what wavelength it is. So X-rays, I have told you it is in Angstrom. So X-rays will be 10 to the power minus 10 meters. Infrared, it's slightly longer. Okay. Or you can say AM radio waves, you know, it will be in kilometers, radio waves or meters. So radio waves will be 10 to the power 2. Microwaves will be in millimeters. So millimeters is somewhere here. So B will go with 4. Infrared will be basically your, actually, you can also get microwave here, and infrared will be somewhere here. My bad, sorry. Infrared will be this. Microwave will be 10 to the power minus 2. That should be the answer to this particular thing. A is with 1. A, yo, options marked are wrong only over here. Options are wrong. Guys, this is not the correct answer. Okay, like I'm telling you, AM radio waves will be 10 to the power 2. X-rays will be 10 to the power minus 10. Microwaves, you can say 10 to the power minus 2. Infrared, 10 to the power minus 4. You can say that. Okay, so that's what the option will be. Okay, these kind of questions are there in the exam. I can keep one question as homework for all of you so that you can solve it. So try to solve this as homework. I want all your answers in the comment section. Answer in the comments. Okay, whether you are watching it live or recorded, doesn't matter, but put it on. Okay, just have to arrange it. So these are the common type of questions, but sometimes they can ask you the applications or the manner in which you get these wavelengths or frequencies. So please go through the table which is there in NCERT. That is very important. Also, you should know the approximate range of wavelengths. From wavelength, you can get frequency. Approximately range, not the exact, but visible light, you should know 400 and 700 nanometers. That much is more than sufficient to solve all these questions. What a lecture today. We had a beautiful time, wonderful time, almost how many hours? 3 hours. Yeah, 3 hours today. And we have completed electromagnetic waves in detail, okay, including energy density, including intensity, including power and its relationship, and all the even three-dimensional questions, some PYQs, wave speed, Ampere's law, Maxwell's equation, all of this, displacement current, we have done it. Okay, so this chapter is done. This is guaranteedly giving you 4 marks at least in this year JEE Mains. Thank you so much. Do not forget to like and subscribe. This was your Captain Shreyas signing off. Bye bye. Take care.